See, modern data is huge. In the early days of computing, we dealt with toy problems, a few dozen data points that a human could check with a pencil. Today, matrices aren't just larger, they have reached a scale where they exhibit entirely different mathematical behaviors. So, so basically, the idea is that we have transformed from toy problems to scale driven intelligence. So now let us see why the transition to the large matrices changed the world of technology. So first let us look at the scale of reality. So modern data sets, they are wide, they contain many features, and they are tall, many observations. So the modern data set, it is massive, wherein it has got lots and lots of features. It is wide, it contains many features, and it is tall. It contains many observations. So the world we are in, we are talking about millions of users. A recommendation matrix for Amazon or Netflix, it is not just big, but it is sparse. Meaning to say that millions of rows and columns are empty. Like 99% of that matrix might be empty. So a recommendation matrix used by Amazon or Netflix is 99% empty. Now linear algebra provides the tools like the sparse matrix storage to handle this without crashing the system. Now, the world we are living in, we are talking about billions of parameters. The large language models like the GPT-4, they are essentially trillions of numbers organized into matrices. So these large language models are basically the trillions of numbers. Every word generated is the result of these massive grids interacting. So every word generated by a large language model is a massive grid interaction. The world where we are living in, we are dealing with high dimensional data, high dimensionality. In biology, a single DNA sample can have 1 lakh plus variables. And that is what the curse of dimensionality is. Because 1 lakh plus variables or samples is where the traditional statistics break down. And here, high level linear algebra comes into the picture. We make use of dimensionality reduction to reduce the dimensions. And for that, we make use of high level linear algebra that can find the signal in the noise. So now it's very clear if we talk about the scale of reality, the real world where we live in, we are dealing with, the systems are dealing with millions of users, billions of parameters, and high dimensionality. And linear algebra is playing a role. And also, we are realizing the importance of large matrices. Why do we need large matrices? Now, the next important point is the four massive challenges. The four massive challenges. So, the first massive challenge is the computation challenge, the work problem. So, standard matrix multiplication takes big O of n cube time. If you double the size of a matrix, the work does not double, it increases eightfold because it's n cube. Now, the goal is we need algorithms like the distributed computing that can cheat the physics of computation to get answers in seconds rather than years. So, for that, we need large matrices. So, computation is a very big challenge. So, now the idea is very clear that if we are dealing with large matrices, computation is the bottleneck. Like we see that the traditional matrix operations, the standard matrix operations, they are the order of big O of n cube. So we need some sort of distributed computing algorithm, some techniques wherein we can optimize the computations. Now the second very big challenge, the massive challenge is the memory, the space problem. A matrix of 100k cross 100k array, floating point numbers would take roughly 40 GB of RAM. Just imagine if we are dealing with a very big matrix of 100K into 100K, and this matrix is holding floating point numbers, then it will occupy 40 GB of RAM. It will need 40 GB of RAM, which can be very huge. So experts, they make use of matrix factorization and quantization, turning 32-bit numbers into 8-bit or even 4-bit to shrink the footprint of the matrix so that it can fit on a smartphone or a single GPU. Now the third massive problem, the challenge, is the speed, the latency problem. So for self-driving cars or a real-time translation, the speed can be a bottleneck. The math must happen in milliseconds. So if for real-time systems and for self-driving cars, the math must happen in milliseconds. So the goal is real-time parallelization. So large matrices matter because they are perfectly suited for GPUs. GPUs can carry billions of simultaneous computations. So GPUs can calculate thousands of dot products at the exact same time. And the fourth massive challenge is the numerical stability, the accuracy problem. When you multiply a billion small numbers together, rounding errors, they might explode. A tiny error in the 10th decimal place can snowball into a completely wrong answer. So rounding errors might explode. So the goal is we use advanced decomposition like the QR to ensure the computer stays stable and the AI does not start hallucinating due to math error. So that is the idea. So these are like the four massive challenges when dealing with the large matrices: the computation, the memory, the speed, the numerical stability. And we make use of large matrices to deal with this problem. And linear algebra has got the tools for it to deal with these four massive challenges. Now let us look at the shift in the perspective. So basically, we have seen a shift in the perspective, like from calculating a result, calculating individual numbers, to architecting a system. When we are dealing with large matrices, we stop worrying about individual numbers and we start worrying about the flow. We learn to treat a matrix like a massive pipeline of information. So large matrices, we should treat it like a massive pipeline of information. So clogged pipe is slow AI. So if the pipeline is clogged, inefficient, the AI will be slow. If the pipeline leaks, the pipeline is unstable, then the AI is dumb. So the bottom line is we don't study large matrices because we like big numbers. We study large matrices because scale is where intelligence emerges. So we study large matrices because scale is where intelligence emerges. So now the idea is very clear that the modern data is huge and we have to go for large matrices. And the good thing is that the modern AI hardware, the GPUs, the TPUs, they support large matrices. They can carry out billions of matrix operations simultaneously. And when we consider large matrices, we are thinking, or we are considering the complete system. And scale is where the intelligence emerges. So this is the importance of large matrices.